you give with a fixed high and low time. So the high time and the low time. So whatever that fixed duration is called, we call this width. So the pulse width, that is a pulse width. You'll understand the basics of it. And other parameter is the setup and hold time. Okay. So here, when you look at a sequential circuit that is flip-flop, so to the flip-flop, what is the input? That is data in. Data in is the input, and you are feeding the clock. Now, with respect to the clock, now the flip-flop has to sample the data, that is input data, and then pass it on here. Okay. So now what happens, how it works, right? Now in this pause edge of the clock, now you have made a design sensitive to the positive edge of the clock. Now if you look at, now just I slide through one of the okay, for your understanding, that also I will explain. For example, now um, okay, the Verilog code. So here, always at pause edge of clock, right, or neg edge of reset, you have your processing. If reset, right, you here two flip-flops are shown. So the first flip-flop output Q1, right, is assigned with D1 with respect to the, if this is a synchronous reset, if reset, both are, both you are making Q1 and Q2 0, that is one part. Else when this procedural block will get activated, when it gets the negative edge of the reset or positive edge of the clock, in both the conditions it enters here. So now when usually reset will come first you will reset the system. After that you bring it out of the reset, then the circuit has to work with respect to the clock. Now initially during reset, both the flip-flop outputs you are making 0. Then the next time, so passage of the clock, D1 you are giving to Q1, Q1 you are giving to Q2. So this you are seeing non-blocking assignment. In synthesis class, we also saw this. When you put blocking, what happens, how the circuit will be realized. When it is non-blocking, how it will be realized. Synthesis code, Verilog code we discussed, right? So that way, this is the circuit what you have written. When I was explaining flip-flop, I thought it is more clear. This test pen, don't bother. So now the same, if you look at here, Q1 and Q2, so it works with respect to the clock. For example, see here, the clock passage. Now the D is 0 here, D is 0 here, that is D1 is 0. Q1 will be 0 here. Q1 means this one will be 0 here. And next passage of the clock, only it enters here. Okay, now before that reset would have happened. See, for example, now reset is 0. During that, all are becoming 0. That is first thing happens. After that, edge of the clock, D is sampled, and then you get Q1. Now at that time, Q2 also is working with respect to this clock, where it is passing D2 to Q2. Okay, what was what was D2? D2 means it is Q1, because there is no combo logic here. Okay, so Q1 is equal to D2. So that way Q1 is equal to D2. 0 is passed to Q2 as well. Okay, in this edge, both flip-flops are active. Okay, and next flip-flop, right, next edge, you see D is 1. Now Q is 1. Okay, Q is 1. Next is, you see Q2 is 0. Why Q2 is 0? Because in this edge, it is sampling Q1. Q1 is 0 here, previous past input, because it has changed to 1. This is the future. This is currently it has updated, but it has not passed to Q2. This will be passed in the next clock. So in this clock, next clock, D1 is 1 and Q1 remains 1 because it was 1 earlier, but Q2 is changing to 1 here because the Q2 is sampled. What is the input for Q2 flip-flop? D2. D2 means Q1. So this Q1 is passed here. I am showing with the real simulation time here how it works. will also, we will show some with some other waveforms. So what is the takeaway here is now how the synchronous circuit, the flip-flop timing works here. Okay, so now all these delays, right now, what is the delay from D1 to Q1, D to Q2, right? All these right now, they are ideal. I have not considered any delays. It is a functional simulation. It's a functional simulation. I have not considered any delays here. Okay. So now with this background, okay, further, here itself, if I want to explain the setup time, the setup time is before the edge of the clock. Now, how much time the data is stable? Data means D1. Now, here it was 0. Okay, it is easy to explain here. Let us say this is positive edge of the clock. Before the positive edge of the clock, D has to be stable for some time. What is the time, minimum time it has to be stable as 1 in order for it to be sampled here to pass it on to Q2 is setup time. And after the edge of the clock, you see for some time it is on, okay, and that is the hold time. The minimum time the data has to be stable after the rising edge of the clock, after the sampling edge of the clock, right? Because at times you may go with a design of negative edge sampling. Okay, your instead of positive here, I give neg edge, right? That will become a with respect to negative edge of the clock, you need to look at the setup and hold. So in this clock, this is setup time because this, and after this, how much it has to be held. Now every clock, every edge, this is the analysis. Any edge, for example, now D, I say setup time is 2 nanosecond. This input is coming at, let us say this gap is only 1 nanosecond. Now that is called setup violation. Okay, so so that is what is the main theme of the synchronous circuit and the analysis. Now what I did is dynamic timing analysis. Dynamic timing analysis I am doing because with respect to time, over a period of time, clock period is, let us say 10 nanosecond, 100 megahertz clock I am running. Every clock I am checking whether any of the data coming in is not meeting the setup and hold criteria. Okay, so now this is what is called dynamic simulation. And the same when you do it with delays. Now this is done without delays. With delay means what? I say to pass data from D1 to Q1. Actually, with respect to flip-flop, we consider clock to Q delay. Clock to Q delay, let us say 2 nanosecond. Because you have seen all the library cells, sequential cells, flip-flops, there will be timing arcs, which is clock to Q delay. Let us say 2 nanosecond. Now with respect to the rising edge, after that, before it gives the output, that is Q1, it will be coming after this delay, that is clock to Q delay. That is, if I say 2 nanosecond, you see the output Q1 from the edge of the clock, not from D, from the edge of the clock. That is why clock to Q delay. Okay, so it will be 2 nanosecond. So now that is what when you do with delays, that is standard delay format we use. After place and route, we extract the file called standard delay format, that is SDF file, and we will annotate those delays to these flip-flops and run the simulation. That is gate level simulation, we call GLS. Okay, and this functional simulation only with the gates, it is one level, that is 0 the delay simulation. Second is with delays, that is gate level simulation with delay plus timing, that is SDF. So now both of these, right, SDF, so this is called dynamic simulation. Okay, so in dynamic simulation, we run the simulation and then check whether my circuit is meeting the time. Okay, so that is one thing. Now the setup and hold, what I showed here, this one right now, before the edge of the clock, the data must remain stable at least for this much time. This is setup. This is an expectation from this flip-flop, right, library vendor, that okay, the data has to be stable. In case if it is changing here, sorry, here, right, I am not guaranteeing the output. I don't do anything, but I don't guarantee the output of the first flip-flop. Now that is after the edge of the clock, whatever. See, normally signals are shown like this because it may be going from low to high or low to high or high to low. That's how in that representation the data is shown like this. You need not have to get confused why this are okay. So that is the understanding of setup time and hold time. So this is very important concept, right, in the timing analysis in your STA also, okay, and the basic things. And pulse width also, there has to be a definite pulse width, because you see, if the pulse width varies, let us say the clock is 10 nanosecond, a high time is 5 nanosecond, low time is 5 nanosecond. Because of some change, if it goes to 4 nanosecond, if the hold requirement is, let us say, 2 nanosecond, right, you are reducing the hold window. So that way, very important pulse width also. So setup time, to explain in a definition, it is a setup time is the time interval before the active clock edge during which the data should remain unchanged, right? So this is the one, very important. Whole of your digital design timing concept is standing on the basic these three things. Okay, further they are all evolved, after this. Hold time, the time interval after the clock edge. See here, active clock edge, it could be high or low, okay, but here in this case it is rise time. So time interval after the clock active edge during which data should remain unchanged. Minimum time after the edge of the clock, I expect, see, if it let us say I expect some 2 nanosecond here, so data changes here itself, means this is shifted here. Then also I say it's a hold violation, I don't guarantee the output here. Similarly, this setup also, here also, let us say I'm just taking an example, it could be 1 nanosecond, 2 nanosecond, that library vendor will define. So it's a window. So now if this is, let us say, only 1 nanosecond, the data changes here, then I say setup violation. Okay, so then also I am not output, normally I drive X. That is also models that, okay, this may be 0 or 1, unpredictable, don't rely on this. Okay, so that is what will be given in the dynamic simulation, whatever I showed you. If you are doing a timing simulation and if the numbers are not meeting, then you will drive, instead of definite value 0 and 1, what you saw in green color, you will see in red color X, which is an unknown, right? X means there is nothing called X. It is just the state, whether it could be to represent saying that it may be 0 or it may be 1. That's it. What is X means? That is in simulation. So these three important criteria, parameters. Now, this is also very important concept. See, you always say, this is the frequency this chip works, right? What is the limiting factor? Always I wanted to have the maximum frequency in the order of gigahertz. What is limiting me, right? So now that analysis, if you want to do, it is the maximum frequency, right, which the timing the particular circuit works. Now that is determined by couple of factors, right? Typically any design, it is this structure. So in the whole ASIC, you see this kind of structure. There is sequential, and in between there is combinatorial. This is a multiplexer, combinatorial. Some AND gates, OR gates, all these decoders, encoders, all will be in this. And the output of are some multipliers, adders, all in between. I'm not saying only 2 flip-flops, there are millions of flip-flops. So all will be there, right? So in the chip. Now, if you dissect every gate, every flip-flop, finally you will arrive at this. And finally, you will have to make sure for every flip-flop, output, whether it is correctly passing on to combinatorial logic, further from combo to one more sequential, is it going fine? This also called, let us say, this is registered. It's a register, 1-bit register. let us say this is a registered output. Okay, so that's how we call. So now in static timing analysis, right? So you will do all these calculations, right? And what are those delays? And you will analyze the circuit by not simulating. What I showed is simulation. So here by not simulating. So let us understand what are the high level timings parameters you will get. So like I told you there, this is T width. Okay, one high pulse, one low pulse. This is width of the clock or the clock period. Let us say, let us say it is 10 nanosecond. It is running at 100 megahertz. Now, T1 here, T1 is this. It is D is input. It can go any way. Okay, no problem. Now, Q naught, you see, Q naught, in order to pass D to Q naught, there is one timing which we'll consider is clock to Q. Okay, so this is our D flip-flop delay. This is a D flip-flop. If you consider, it's a flip-flop delay. Okay, we consider this flip-flop delay. Okay, and after the flip-flop delay, you see Q naught. Q naught is changed here. Now, after this Q naught, multiplexer delay, you know the multiplexer structure, there will be AND gates, and then finally, based on the select, you will have this structure, and multiplexer delay Tmux. Okay, and this is Tmux, this is one delay, and another delay is the setup time required for this flip-flop. The setup time TSU of second flip-flop. So here your TW, the width or the clock period, should be able to accommodate all these delays. Or you can say TW cannot be less than what? The flip-flop delay, first flip-flop delay. Sorry, I5. Okay, so what it cannot, so TW, anyway, I have it there. I will show you. So TW should be, right, greater than or equal to maximum D flip-flop delay plus maximum mux delay plus setup time of second flip-flop. Now, this is what limits the clock period. Now, your frequency is 1 by T. Okay, now this is the bare minimum, right? There will be some clock skew and a lot of clock uncertainty. There are other things which will come. Those are, comparatively, small numbers. But the important delays which will be considered for the timing analysis are the clock to Q delay and the combinatorial delay and the setup required. Okay, so further, Shravanti will explain, taking launch path, capture path from here in STA terminologies, but understand this basic, these things. Now I have these delays, okay, for this circuit. Now, can you tell me, right, for this flip-flop to this flip-flop in order to pass the data, right? What is paths from Q1 to Q2, Q1 to Q2, okay? Q1 to Q2. Can you tell me the timing delays? I have it here. D flip-flop delay I have given. This is the propagation delay you can take. This is setup time of first flip-flop is 5 nanosecond. Setup time of D flip-flop, this is 5 nanosecond. Okay. And from Q1 to, so the propagation delay of the D flip-flop is 20 nanosecond, right? JK flip-flop timings, setup time required is 25 nanosecond. Setup is 10 nanosecond. Propagation delay is 25 nanosecond. Hope you are understanding. AND gate delay is 12 nanosecond. This one. OR gate delay is 10 nanosecond. Can you tell me what are the delays, right, which are included in order to check the maximum frequency of this circuit? Paths from Q1 to Q2. Consider paths from Q1 to Q2. Can you tell me quickly? Let me check your understanding, whatever I explained. So this is propagation delay. right, of the D flip-flop and setup time of D flip-flop. So this is JK flip-flop, propagation delay means clock to Q, and 10 nanosecond is setup time. Okay, so what are the things you added? What are the things you added? Gate. Which gate? Which gate you added? AND gate, D flip-flop, TSU of JK flip-flop. So take from this path to this path. See, this path to this path is 1. You can split. And then from Q1 to this one, you can split. If you're starting from here, right, clock to Q, D flip-flop, plus, see, here, this is AND gate delay, which is going to K input. This one AND gate delay plus setup required for JK. That is 1. If you want to analyze for this, right, you can consider now setup time. It will, you will not analyze. So now from here, clock to Q delay plus something. That's why I clearly told it is from Q1 to Q2. Q1 to Q2, you don't consider setup of first flip flop here. Okay. So now that is how you can calculate the maximum frequency of this. Is a very typical, any digital engineer should know this concept. How do you determine the maximum frequency of this thing? Whether you have done it in STA, PD, or Verilog, this is a must understanding for all of you. Hope you are clear. So that's how you add up all these things, and now so there are some equations for setup and hold. So we'll see derived from this. Okay. So those calculations will do more, including this one. So here the back-to-back flip-flop and this. Okay. So this clock skew also will be discussed further in STA, where there is a difference in the arrival time of clock to clock 1 and clock 2 in a circuit. So whatever difference from clock 1 to clock 2 is clock skew. So that is the clock skew part. Okay. And so this is because there will always be delay, right? So no, JK flip-flop delay will not be included when you are considering the path from D flip-flop. Okay. So clock driven from some central this one, and see, normally in a chip there will be clock source which will be supplying clock to the whole circuit within the chip. So then you will be suffering delay here. If you look at this delay, because of that, then there will be difference in arrival time of the clock. Then you will try to fix it by adding delays and all. That's a CTS part in the PD, clock tree synthesis. In the clock balancing, all these things will come in the PD flow. Okay. And so that is bit about skew. So now how to fix timing issues, right? All this more in detail, it will be discussed. Okay. So here I don't talk. So one another thing I wanted to explain is the metastability. What is metastability? Now I explained about setup time, hold time. Any violation occurs, because of that violation, output is indeterminable. That is what is the metastability state. So why it is called metastability is, for a brief amount of time, the output of output goes unstable. Okay, so that it will be struggling to settle down either 0 or 1. Take 0 or 1 logic. So that is what is the metastability state. Here, example given, let us say this is one clock domain, clock A. So this is the other clock domain, clock B. So definitely any input coming here, this clock is learning a different frequency. This is a different frequency. Okay. So now, asynchronous input. Now, in order to the asynchronous input, when you are sampling with respect to the pause edge, right? With respect to pause edge. Now, if you look at D, is changing exactly at the positive edge of the clock. Positive edge of the clock, D is coming. Now, I am not sure whether it in a way I expected this to be coming somewhere here, so that meeting the setup time required for this, sampling. Now that is an asynchronous input, anytime it can come. Okay. So now with this, you will get the output which is not predictable. So, and then what you do, what is a fix for it is I pass through one more flip-flop. That is, this circuit is called double synchronizer. I pass through one more flip-flop in order to get a confirmed stable output. So finally, what is my assumption? The first flip-flop output, right, when it has sampled a synchronous signal, it will settle down either to 0 or 1, at least after some time. Now that settled value is what I pass, right, to this flip-flop in the next clock. See, in this clock, what happens? The DS is stable. For this flip-flop, what is the input? DS. DS is stable and it is settled at 1. That 1 I sampled. Now the output at D out is good for me. Good means stable. Okay. So now this is one of the way how we fix the double synchronization. Using double synchronization, we will fix a metastability issue. One thing. So the second thing is,
sir.
Yeah.
Excuse me, sir.
Yeah.
Here you are assuming to settle down some specific time of period.
Yes. Yes.
After some period, we are assuming it will be we will get a stable D out.
Yes. Yes.
So you added one more flip flop. Suppose if with that flip flop also,
I got your
if it is
question. With that, I got your question.
if it is not stable, if you
add
get
one more, a blunt answer is one more flip flop you add. So basically, what is the logic? What is the logic here is, see now
like that every time we have to add one more flip flop, or specific only double synchronization means only with two flip flops. Can't we get any kind of this disturbed input to get reach a stable output at destination flop?
I got you. No. I got. I'll clarify. See, basically, now see any signal, right? So it cannot be unstable for a long time. Okay. Now, wherein let us say high precision designs, and you wanted to double ensure that it may take more than even one clock to settle down. See what is happening here. Like you see, analyze digitally in digital world. Okay. So now what is happening? Finally, it's a flip flop. Now, if you look at inside the flip flop, what are the things inside the flip flop? It is finally what? What is inside a flip flop?
It's a kind of latch memory. It's a latch for some time and
finally
propagate.
It is having basic gates, correct? Now
yes, basic NAND latch or NOR latch, kind of.
Now based on the input only they are responding here. Okay. Yes. Now whether AND gate, OR gate, and you have anyway inside it is master slave, right? And then now the assumption is that the input which is passed on to the output, right? It will definitely become not stable. It will settle down to one value within one clock period. Okay, that is one assumption. Now, like I said, in case if it is not, still you can add high precision. You can add one or flip flop. So otherwise, typically with double synchronizer, it will work and it should fix the problem. Okay.
Yeah.
So further,
how do we know?
Right, you can study more. Let us know.
Okay, sir.
No, let us not argue. So you study further on that. So that is what is my explanation. Okay. Otherwise, it will never end.
Sir.
Okay. So double synchronizer, triple synchronizer, or one more. Right. See, let us go with some logic. Okay. So that is how industry using, and also I explained further digitally. Now I will tell you. Go to the transistor characteristics. What is inside that AND gate? Transistor, go and study the transistor characteristics, how the response time, any input changing, how much time it will take. See, that is how. See, you can go in depth and then analyze, right? Why, how, all that. But at a digital level, in fact, I am explaining this at a deeper level, right? So because this itself, is not in the STA part. I'm explaining as a fix because metastability you may or may not study. So let us go with this. Okay. So I know the industry practice and we have used it, right? And when you say how, there are billions of chips working in the industry with this logic. That's all I can say. Proof, right? So further, like somebody analog, somebody Venki or someone has gone deeper into analog. So he is talking about MTBF, right? So those are the kind of things. Still, you go to the characterization and then transistor level you can study. Okay, so that's the thing. So further we can go. So that is about the metastability part, and this is the fix for it. Okay, and how to arrest metastability, like this is the one fix. And of course, if there are many signals, right, you can use the FIFO. Okay, so FIFO normally we use it's right, usually we write the data. Let us say 8-bit you want to synchronize. Okay, so 8-bit when you want to synchronize, you pass to, let us say, depth. Here also the same logic. For 8 bits, if you define 2 depth, FIFO depth as 2, then it will go through every bit, it will go through 2 flip-flops. So if you say depth 3, it will go through 3 this. So many times especially so when there are more than one signal, they go for the FIFO FIFO to arrest the metastability state. Okay, and this is about the basics of timing. Okay, further, further, if you want to explain, I will tell you what all cases can happen. Okay, okay, now the same case you take here, 2 flip-flops, D1 is coming here, Q1 can get, you can get Q1 here itself, case 1. Now in the second one, Q2 is changing here. This is case 1, let us say. In the other case, Q1, you told, no, your own doubt, right, sir? What is the guarantee? All this first flip flop, all the cases we are taking, immediately it may change to 1 is case 1, and it is taking 1 clock and changing, right? Here what happened, it came here, further it moved the output to the next clock here, Q2. This is the second case. Let us say after some time it will go 0 1 0 1 0 1 and finally it's settled at 1. This is the other case, right? In this edge you get this one, and it can happen this way also. See, it may almost getting it to 1, and finally it may come down to 0 and get settled at 0. Now see here, in the first this thing, it didn't get stabilized, but still it moved this thing to one more flip-flop stage. At least it instead of this clock edge, in this clock edge you got the stable output. See, this is how the assumption, right, and the different cases which can happen in the metastability case, or in the first stage output. So here, what is the takeaway? When you are doing static timing analysis, the timing calculations and all, you will turn off the timing checks on the first flip-flop of the double synchronizer. Okay, so because you are not relying on any of this, you are not relying on Q1 at all. It is also called false path. Okay, so in this one, in the design, it's also called false path. What is false path? This, don't do timing analysis on this, because I myself I am very much guaranteed that it is spurious and I cannot rely on the output of the first stage of the flip-flop. Okay, so when you do, in fact, when we are doing gate level simulation also, we will ask the PD team to dump out all the synchronizer first flip-flops paths, write it out, and in a file you give. And when I am simulating gate level, I turn off the timing checks using my simulator on these flip-flops, so that if you don't turn off, what will happen? This will get passed to here when I'm doing simulation as X, and further whole of this pass again from here, one more flip-flop connected, that also goes for X, 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 I will not get any predictable output at all. So that's where I just turn off the timing checks when you're doing static timing analysis. When I'm doing dynamic timing analysis, that is using gate level simulation, where I am checking the functionality also, I turn off the timing checks. Okay. So that is about the metastability and the basics of the timing. Okay. And anyway, this is some English related to that. So basics of timing. So I just explained about the STA and the DTA. DTA means dynamic timing simulation, timing analysis. This is basically done using gate level simulation. Like I told you, I explained the waveform. That's a functional simulation without timing. If you are if you have done the simulation with gates with delays, okay. So that is the timing analysis you would have been doing. Okay. So basically, what is the difference between static timing analysis and dynamic timing analysis? Static timing analysis, whatever, let us say, maximum frequency of the clock we calculated, I gave a table of the delays. Based on the delay time, now we also arrived at the equation, what is the setup required, what is the minimum hold required, and the maximum frequency. Those calculations doing without simulation is static timing analysis. You're doing the timing analysis of the circuits with the given timing budgets. Clock period is given, setup time is given, hold time is given, then whether it is meeting that particular frequency. Now you saw that if the TW, if those delays are more, it will spill up to one more clock. At that time, now you will have to say either fixing that could be increasing the clock period, that is lowering the frequency of the circuit, right? So that could be a easier fix, but otherwise you don't want to reduce the frequency. It is designed to be working at that frequency. Then you will go for other optimization techniques to fix setup and hold violations. So basically, all that here, static timing analysis is you are sitting there and you are calculating how much time it takes. Let us say you want to reach from Hyderabad to Bangalore. What is the time it takes? You are sitting there and calculating. It's budgeting, maybe based on your experience or with previous travel or whatever, and you will calculate from Hyderabad, right, to this thing when you're driving on road, reaching from one city to other city, how much you split up, and you see, okay, from reaching from Hyderabad to leaving the city itself, I take this much time. From Hyderabad, I don't know what and all cities you get in between. City 1, what is the time? City 2, what is the time? Then near Bangalore, this one near airport, right? So like that, splitting the whole of these path into multiple timing arcs and analyzing and making sure that, right, the you reaching at the right time what you budgeted. Let us say from there to here you reach at 5 hours. Now you are calculating and you are not traveling, you are calculating. But real travel is dynamic. Let us say dynamic means you are coming to Bangalore, and then after coming here, you saying that, okay, I took 6 hours. Okay. Now, real time, is with functionality is dynamic analysis. Now, this is calculations with a budgeted time, because these timings are given from Foundry, right? And that way they are more accurate. And if you do the analysis with respect to that, and more or less or almost same, you will still reach at the same time. Okay. So that is the static timing analysis. That's why it's called static. You are not traveling, right? It is not dynamic. Dynamic means simulation. So here, no input vectors are required. Okay. So you are not applying any test vectors here. But here, I am applying test vectors. You saw the waveform, functional, same this thing. I will apply test vectors and D input. Test vectors means what? D input I have. I apply D input, and then I see that whether it is passed to Q1. Right. That is what you do in the dynamic simulation. That's where in the chip design, when you are doing the system level verification, you don't do the dynamic analysis, that is gate level simulation for each block. Say, let us say SOC is there. In SOC, multiple blocks are there, and block 1, when you are designing, block 2 design and verification you are doing, you don't do the gate level simulation for this only functional simulation you do. But gate level simulation you perform when you are doing SOC level, where you see that if this is the processor, from processor, whether the path is okay, whether from processor this one, all these you select some test cases for each of the data paths and then run in gate level, right? And then make sure the functionality is okay with gates with delays. Okay, that is dynamic. Okay, and you apply test vectors. That's what I wanted to tell. So apply test vectors means you are giving the stimulus simulation. It is faster since it doesn't involve simulation. So it's just how long it takes for you to calculate, right? But at the same time, how long it will take you for you to travel? Same same way you can relate. Okay, so now it is slower since it consumes simulation cycles. Okay, this one doesn't involve simulation, so you're not simulating, you're not checking over a period of time. Okay, suitable for complex designs, right? Of course, STA, right? However big is the design, now whole of this you have STA tools, timing analysis tool, we have Cadence, the Tempest tool, which will divide the whole circuit into multiple timing arcs, and those timing arcs it will analyze with respect to the given timing budget. Okay, so okay. So static timing analysis is a method of validating the timing performance of a design by checking all possible paths for timing violations by not simulating the design. Okay. All synthesized designs are broken down into multiple timing paths. Each timing path has a start point and end point. There are only two types of start points in this one. This Shavanti will cover more: input port, clock pin, right? All this, and endpoints, data input pin, output port pin. Basically, from where to where, right? That's what. So different timing arcs, cell delay, right? And see, at times I face questions, sir, only combinatorial circuit, can't I do static timing analysis? Now, this background should help you. What was combinatorial here? What was sequential? Now, if you do static timing analysis on the combinatorial circuit, what does it mean? Right? Combinatorial circuits, the present outputs are depending on present inputs. Okay, so that is cell delay and net delay, all this. So that just these delays you will sum up and then you will do. So if you look at typically, right, any circuit will have this kind of combinatorial and sequential path. This is for given. Okay, so now all this you look at, I have mentioned in my own cryptic way. This is one timing arc. Let us say input to clock path. This is, let us say, one timing arc. Now clock to clock path, another timing arc. Now clock to output path, another timing arc. Now AND gate delay. Now this net delay. When you have taken a physical database, then net delays also will be added. And then XOR gate cell delay. And now XOR gate output net delay. And here it is coming to mux delay, and even this net delay. Then this setup time of this D flip-flop, right? So like that, the circuit is split into the multiple timing arcs and flop to flop, right, within one clock domain. STA is performed only within one clock domain. You have design with this one clock domain, this one clock domain separately. This it will analyze, this is will analyze. So passing any signal from one clock domain to the other clock domain, static timing analysis will not check. That's a limitation of the STA tool. Now that's where we use other tools like CDC, clock domain crossing tool, CDC tool. Okay, so all those we will do. So now more of it. STA is all about this calculations and taking the delays into consideration and checking few more this thing like setup slack, hold slack, all this, right? So that's about it. Okay, so without simulating, how will you know the functionality of the system? Basically, now functionally RTL simulation you would have done. That is where one level of confidence you have. Like I told you here, after SOC is integrated, SOC all blocks are integrated, you will select for each of the data path one at least key test cases. Let us say in a particular SOC and block level and all, you have 1,000 test cases. At the gate level, you select some 50 test cases which are critical, which covers all the paths. I have one slide for gate level simulation, so in case towards the end I will show you where why gate level simulation. And of course, this is one of the thing is to check the functionality after translating into gates. Timing is added, whether my functionality is meeting or not. Gate level simulation is done. Okay, but we will not cover entire functionality. Okay, so at the high level functional we will be doing, but gate level simulation, through gate level simulation, you cannot do the timing analysis at this granular level, taking every cell timing arc. So we do the static timing analysis, one level, and dynamic simulation gate level also we do for for getting more confidence level. Okay. Hope Manjula I answered your question. So little bit more. Okay, I got some beautiful diagrams here to explain, so I added this as well. So minimum time data, the same you see here. Valid data, clock is there, setup time, hold time. Okay, so always we analyze the data in and the clock. Okay, so that is the setup and hold. Now Shravanti will explain about data arrival time. What is data arrival time? See, if you look at, this is Reg 1 and this is Reg 2. Okay, so I leave this. I think the demo is available, and this particular thing you can explain if the time. How long it will take, Shravanti, for the demo? Half an hour?
Yeah, might be like I need to invoke the tools and things, right? So I think it
Yeah,
might
yeah.
take
So
about
I think
20
we
minutes.
will shift with this introduction. Hope the timing part introduction I have given more into data arrival time, setup slack, hold slack, all that we will discuss after this demo today or in the next session. Hope the this thing is okay. Okay, Shavanti. So I am done.
Okay.
So now you can.
Okay. So this was the environment set by the Mobex term application for you guys. So now let us see like how you can access the RTL files and everything. So once you get into the environment, you will be with your username as such. Like according to my name, it was given the access as such. So you will be into this particular terminal. Now under this, so you can see this asterisk, right? Small symbol. Okay, so you can just see this as symbol. So this means, right, you are in the root directory or the home directory of this access whatever you are given. Now here as of now we have not enabled the data to anyone. So once I once the data will be enabled, you will be seeing such kind of directories or the folders inside this home directory. So here, if you want to know the contents of this particular directory, you can just give ls. ls is used for listing the content of that particular directory. So I am giving ls. Here you will see a tar file. Okay. Here you can see a tar file, right? So this is what we are enabling to you people. So you'll get a tar file in this format under this directory structure. If you want, you can just give ls there. So ls is the listing of content of that particular directory. So pwd is present working directory, like where you are working on. So I am working under home, inside home, I am in my directory. So PWD is for present working directory and LS is for listing the content of that particular directory. Now, under this directory, I have a tar file called synthesis.tar.gz. This will be given to you guys. Now, if you want to extract this file, the command is tar -xzvf So tar is the command, and you're giving us which you can just do man on that particular command. What is that doing? So and give the name of synthesis.tar.gz. So if you're executing this command, you will get a directory or a folder called as synthesis, as you can see. So once you execute this command, then only you will be able to access synthesis directory. You can't access or open the files which are in zipped format. So I hope it is clear till here.
So just to add, basically tar is a command which we use in Linux or Unix for zipping. Okay. So in WinZip, whatever you have in Windows, so in order to compress the file, okay, so the tar utility is used, right? And then so there are options, tar CVF for tarring and for tar XVF for unzipping, right? So this one, Shravanti, are we not copying the folder itself? Do they have to untar it?
Yes, they need to untar it. We are forwarding the.
No, sir. No, sir. We will be copying folder itself.
Yeah, folder itself.
Okay.
We will be copying the folder. They won't require to untar it.
Okay. So let us make the beginner's life easy.
Okay, then. Okay, if they are enabling the directory itself, then you can just see the directory which I extracted already, called with the name of synthesis. Okay. Now under this particular root directory, I have this synthesis directory. Now I want to enter into that particular synthesis directory. So how do I enter is you need to change the directory to the synthesis directory or the synthesis folder. So the command to change to the synthesis directory is cd space, and you can give the directory name. Okay. So cd space synthesis. If I'm giving enter, you can see you are inside the synthesis directory. Okay. So here, whatever the name convention it is showing, that means you are in that particular directory or the folder. So this is what we are providing you the content. Again, I am doing listing at this particular directory. I am executing a command called ls. Okay. Okay, I'm listing the contents of this particular directory ls, doing a command. So under this, you have this particular directories or the folders with the name assignment, cap table, left library, and logical synthesis. In the same way, using the cd command, you can go into each and every directory and check the files in that particular folder. So as of now, I'll show you how you need to execute logical synthesis. So I'm entering into logical synthesis. Okay. Now inside this, I have the RTL folder, SDC folder, and a work folder. So inside RTL, I have put a RTL file that you are going to execute. Okay. Now to open this file, you can just use the basic editor command, that is gedit. So if you want to open that file, RTL file, and just check the content, you can just give gedit space the file name. So file name, I'm just giving it here. So basically cd is a command to change the directory. So to change the folder, you need to give a command called cd, and to see the content of that particular file, you can open with an editor, gedit any of the files. It might be sdc file, it might be an .v file, or it might be any .lib file also. You can access the editor called gedit, so that you can just open that particular file. Okay, you can see it got opened now. So this is your RTL file. Okay, so this is for the logical synthesis purpose. I have forwarded the RTL file of UR design itself, like how I have showed the demo for the UR design. Okay, now if you want to come out of that gedit environment, just press Ctrl C. So I'm closing that RTL file. Okay. Now I am inside RTL directory. Now if I want to come back to the synthesis folder where I have started my process, so if you want to come back, you need to give a command called cd space dot dot. Then you will be in the directory of logical synthesis. So now you are in the directory. If you are giving one dot dot, that means you are out of one previous path. So now if you want to come out of logical synthesis, again you need to give cd space dot dot. So now you are in synthesis directory. So likewise, to enter, you need to give the folder name. To come out of that folder, you need to give dot dot. So when you are entering some path, it is called as absolute path. When you are coming out of the directory, you are giving a symbol called as dot dot. That is basically called as a relative path. So now, as of now, I am in synthesis directory. Now I am doing the listing again, so that you can see I'm entering the logical synthesis directory again. So inside logical synthesis, if you want to enter one more path, I have a directory called as work. So if I want to enter the work directory, I can just give it here itself by giving a slash. So at a time, you can directly enter to the work directory. So cd space logical synthesis slash work. That means you will be in the working directory. Okay, now we are in working directory. See here, I have given you the run.tcl file also. So I'm opening that run.tcl file. So here I have mentioned the script, how you need to run. So it's better, the paths I have set are according to the paths of the working directory. So here I have created the library paths, and I have created the HDL paths and the SDC path, and I've mentioned the script and how the reports are getting generated. So you can check out the run.tcl file also. It would be better if you are invoking the genus tool inside the working directory, or else if you want to do the process in other directory, you can do it by changing the paths in run.tcl file. But as of now, I am just invoking the tool in a working directory. So that is under logical synthesis. Inside logical synthesis, I have a directory called work. There I am invoking the tool. So I'm just giving genus. So genus is the command to invoke the genus tool.
So right now you synthesize the one which we are putting in the server. So really, if you want to take your design for synthesis, so you can write to cadence support at tentipel.com, and then really, if you want to take that through the entire synthesis process, especially copying the files from our local machines is been controlled, or from the Tentipel team, because it may use a server, right? So if it any malware or virus kind of thing is associated with your file, so then definitely be a problem. So that's why right now, with that intent, copying the files from the local machine is avoided.
Okay. Now, like we are inside the genus tool. So here you can just give the command as I told you before for the sourcing. Okay. So source, and you can just execute the run.tcl file as I have set the paths previously. It is running the implementation process of synthesis. Okay. The process of synthesis is done. So any queries regarding this? Okay. So I think you guys are clear with the environment. In the synthesis directory itself, I have given a file called readme. You can just go back to that synthesis directory, and there is a directory in called as assignment where we have given you just the RTL code. I'll just go back to. So in the synthesis directory itself, we have given a directory called assignment, or a folder called assignment. I am entering into that particular assignment directory. Okay. So inside assignment, I have given an APB timer design where you can only yourself write a run.tcl file and implement the process of synthesis for your practice. Other than that, whatever demo I have shown, I have put it in the logical synthesis directory and the physical synthesis directory.
And one more, Shravanti.
Okay.
So actually, first let them start with the step by step with the commands. So whatever the run.tcl file which you have told, no. So let them do with the commands one by one, so that they will get to know the path how they are setting.
Yes,
So
that
based
I
on
will.
that,
Yes.
based on that, next whatever the assignment work they have given, no. So that they can use a run.script file.
Yeah, obviously they can do that. I've mentioned that in the previous session also.
Yeah, because if they got any error with respect to that part, so it will take some time for them to fix. If once
Yes,
they are
yes,
good
yes.
with
I'll address that. I'll address that. So as I mentioned, in the run.tcl file, I have given the paths from the working directory. So if you want to give the other paths also, you can just give the pwd command from where your path is and copy paste that particular path in your run.tcl file. So your base directory will be the work directory where I have created the paths. If you want to change the paths, you can just give execute pwd command in whichever directory you want to implement, and execute the same path in run.tcl file and run the things. Hope the environment is clear. Okay, any queries regarding this?
So Shravanti, you have copied the library files also. Where are they now?
Yes, inside lib directory, I mean to say inside synthesis, there is a library directory. So cd So inside this
You say
synthesis
LS,
directory itself,
LS,
inside this synthesis directory itself, we have this particular library directory also. So
okay, so
I'm
you
just
have assignment cap table, LEF, left lib, logic synthesis, physical synthesis. These are the
yes,
directories
yes,
under synthesis. Okay,
yes,
lib you
yeah,
say LS. Now
yeah.
you want to go
ls
slow and
will list the contents of lib. Now you can see two types of libraries, slow dot library and fast dot library. I'll discuss in the STA sessions what are these two types of library, in which cases we'll be using these two types of libraries. But as of now, in the run.tickle file, I have given the path that you need to include as slow.lib. You can just change the file name as fast.lib also, and you can execute the file and see the changes in the reports of timing and power and area.
open run.tcl, Shravanti.
Okay.
See, Shravanti is opening from the lib. No, where are you opening from? Lib directory.
Yeah, from lib directory, I'm going one step back. That is the
One
reason
step
I'm
back.
giving dot dot slash.
See,
So
whatever she is
inside,
using is this is relative path. Relative
yes.
path means I am in lib relative to the synthesis. I need to go back one level. This is relative path. Now the same instead of dot dot, you say PWD, Shravanti. Right now, okay. Now, if she says cd complete cut and paste that slash home slash Shravanti dot this one and synthesis, that is she is this is absolute path. Absolute path and relative path means absolute means you are giving the entire file system path, that is absolute path. Now relative path means where you are. Now you are in which directory you are. With respect to that, you are going one level back or two levels, three levels, right? So that is what is the relative path. Now PWD related, right? Now if you open the run.tcl you can open now. So we can
Okay.
see, and someone asked whether I can invoke genus anywhere. Yes, license is set. You can launch from anywhere. But the thing is, now from which directory you invoke, that is the present working directory, right? When you run.tcl, it will consider from that directory. Okay, so that is what is the understanding.
So I am entering into logical synthesis directory. Inside logical synthesis, I have work directory. So there I am going to invoke the genus, or else if you want to give your own paths, you can do that also. So I am doing the process here. So I'm opening the file called run.tickle. gedit is the file name. So run.
Now you remember the home, the what levels are there. Now when we are referring dot dot, you can understand, right, the relative path. This one, how we are giving the relative path. Relative means with respect to the present working directory, how it is related. Is it one level, two levels up, and that is the one.
Okay.
Okay, now
I think now you
yeah,
can see the
now I
run.tickle.
think see whatever she has done here is set db dot init lib search path. The path she is giving is two level going back means up, and there she can now you can show this the same
Yes.
thing one by one when you are executing. Say
Yes.
cd two level, if you go you can see the lib there,
Okay. So
right?
now,
So
because here I have mentioned two paths. I mean to say two levels back. Inside two levels back, I have a directory called lib. Yes. So I'll just go to that particular path and show you, like, is there is a lib there, two sides. I mean to say two levels back. Okay, now I am in work. I have to enter 2 levels back. That means I need to change the directory 2 levels back. So 2 dot dot slash I need to give. Yes. So 2 dot dot slash, inside 2 dot dot slash I have a lib directory. Yes. So I'll be inside the lib directory now. Okay. So here you have the library files. From here I have set the path. So from work directory 2 levels back, inside 2 levels back I have a lib directory. Inside lib I have a file called slow.lib. Okay, what is db in the stickle file? I have already shown you the demo of this process. Like set db is an attribute that you are mentioning. It's a tickle command, basically a tool command, language command, where you can give the path using this attribute. So set db is the command to give the attributes. So and init library search path is the attribute name where I am going to specify the library path. Okay. Now, as I told, like I have to execute the process in of synthesis in the working directory because I have set my paths. Now, if any other command or if you want to change the path, now I need to set the path of the library as this. If you want to set it as an absolute path, just give present working directory here. So present working directory will show me the path. Yes. Now I need to copy paste this particular path. So right click and you can just paste it in that particular path or you can type in that particular path. Okay. So this is how you do the copy pasting. You can just give present working directory at this particular directory and you can just copy the same path in your run.tickle file also. So as a I mean to say, if you're starting off with the process of logical synthesis, you just invoke the tool in the run, I mean to say in the working directory, and just copy paste each and every command so that you will get to know what each and every command is doing once you invoke the genus tool. I mean to say parallelly open genus tool and parallelly open a run.tickle file, and there you can just run the command by command and you can get to know what each command is doing. Okay, this is how you do it in the run.tickle. Any doubts still here? I hope the environment is clear for everyone. Okay, where I'm not clear, can you just... Yes, you need to edit this run.tickle file. If you are using the same file, you can just edit this run.tickle file and you can put it in your assignment directory, or you can just give the path of this particular run.tickle file according to that assignment directory and you can just execute the run.tickle file. So I have given an assignment also to you guys in the assignment directory where I have given only RTL file. You can write an SDC file, you can write an I mean to say the run.tickle file and you can execute it.
So can you open that, Shravanti? Just show it to them. What is that assignment file is?
Yes, I have showed it all. Okay.
Okay. So is it clear to everyone? You have shared it, right?
Yes.
Okay.
So in the synthesis directory, you have a folder called assignment also. So you can just enter into that. CD, I'm changing to assignment. Okay. Here I'm listing the things of the assignment and the file. This is the RTL file that you can implement as your assignment execution process. Yes, obviously you need to change in the SDC file also, because the clock names of the whatever execution I have given for that RTL and this RTL might be different. So you need to change the SDC file also, not the values or the frequency. You can just change the clock name. If it is same, put it as same only. I think most of, like, probably it will be the same clock, the P clock. So yes, if the clock name is varying, you have to change the clock name in the SDC file.
So we are giving the timer, right?
Yes.
So for all your understanding, the design which is given to you is having APB interface and the timer. Okay. So I think I have explained about a system where you have the ARM Cortex processor subsystem and then APB interface. And on the APB interface, the APB timer is hooked, okay, is connected. And design wise, the RTL, the block wise, it is having the APB APB slave. Let us say, just a minute. Okay, so you have this APB interface. The inputs outputs will be APB. Okay, so this is coming from ARM processor, and then now this DUT, what you have given inputs and outputs are this APB interface signals, and for the timer. So inside this APB slave state machine will be there, and there is a timer counter which will be running based on the register set. Here some registers are there. Load the counter, and from that, it will start decrementing. Once the timer comes to 0, then interrupt will come, interrupt output. And also there is this thing to external clock also will be given. That is one mode. External clock can be supplied to the timer. Okay, so there are two modes. So basically now it is having this logic inside, okay, the Verilog code. So now that one you are synthesizing. I think they need to give the constraint for both the clocks, correct, Shravanti? So
Yeah.
P clock
Yes.
G and the external clock
Yeah.
T clock. Okay.
Yeah.
So now okay, how do you submit your assignment? So Shravanti, what is the plan? How they will have to execute that in their user area? They
Yeah.
are modifying the STC files and also other input files.
Yes.
Lib file anyway you are not touching, you are just using.
Yeah.
And Netlist file, RTL file is given to you. So
Yes,
you are
they can just
synthesizing.
forward us the reports. I mean to say the reports of the power, timing, and area, like whatever they have analyzed. So
Yes,
once
exactly.
after optimization, you will generate the reports using some commands like report timing, lint, and report gates and report power, right? So you can just forward us that particular documents, or you can just forward us the reports, whatever you have generated. That will
So
be
we are
well and
having
good.
a
Yeah.
template, right? In order to submit the assignment. So the template, who is taking responsibility to share from multiple team? So that will all be shared with you, the template. So the reports, what Shravanti is asking, right? You can put those snapshot in the report, the template. And we will be appending more assignments in the assignment directory. And as we go along, we will show you, for example, this is synthesis and ST assignments will come. So all those one after the other. So you can do that, and then the reports you can send towards the end. Report you send towards the end. Don't send any intermediate submission. You don't do. So we will not be checking it. So once the course is over, you will be given 1 month time plus 1 week grace period. Within that time, you complete all your assignment and submit as one document with all the assignments completed. So that is what will be evaluated from our end. Okay.
Okay. Yeah, one more small thing, sir. In the like, if you're accessing through Windows PC, in the left side, if you're getting confused with the directory structure or the folder structure, you can just use the GUI also. And inside that, you can get to know like what are the directories. Like left side, if you can see, I'm showing the GUI usage of the
Yeah.
folders. So if you're getting confused, this is particularly we are.
Yeah, you can do that.
Yes. So yes. So inside this synthesis, you can just click on it, and inside this you have this assignment as I mentioned. In the same way, in the terminal and GUI you can access parallelly if you're using Windows. So if you're getting confused with the directory also, just check your paths and the levels according to this directory structure, and you'll get to know the things easily. Yes, you can do the task in the assignment directory itself. It is so okay.
Okay. So we can end session today unless there are any questions, any doubts on the topics which we discussed today, the demo which is shown.
Sir, regarding this static timing analysis for finding the maximum clock frequency, so we have to first calculate the critical path and then we are finding the maximum clock frequency. Is that correct?
So those we will go deeper into it. So I just told the basic considerations for the maximum clock frequency. Okay, how do you go about at a very basic level? So further, there are additional timing parameters which you consider, and then anyway, still another 4-5 sessions, we will be completely analyzing those things. We will clarify that.
Okay, sir. Thank you, sir.
Hello, ma'am.
Yeah.
My doubt is, can I invoke the Genius tool in the assignment directory to run the rend article if I'm writing, if I have a rend article file in assignment folder?
Yes. Yes, you can use the same file. You can copy the same file in this particular uh, assignment directory, run.tickle, or you can just open a file using gedit and you can write your own script in the assignment directory.
Thank you.
Yeah. Yeah.
See, for power analysis, right, we need the switching file. So right now, with the number of libraries, components which we are using, synthesis, either for physical synthesis and logical synthesis, we are getting the power, right? So, but the dynamic power, right, will be calculated based on this one, right? The switching, but it is not part of this one. That's basically power flow. We don't teach that.
Yeah. You can use gedit or vim to open the run.tickle file or to create the run.tickle file. So here you can just give a command gedit run.tickle.
See, unless you know VI commands, you don't use Vim.
Yeah.
Go for gedit.
Yes. So if you are user friendly with Vim editor, because it's again a command execution process, if you are using a Vim, if it will be user friendly because you guys will be used to this Windows, right? So gedit is the best thing. So if you want to open a new run.tickle file, just give gedit run.tickle and an empty file will get opened. So to open the file which is already existing and to open a file with newly also, this command is same. So an empty file will get opened. So here you can just type the commands and execute it. More any queries? Or shall we end the session? I think if it is clear.
Yeah, okay. Thank you all.